Hello everyone, my name is Aldoseri. I'm a PhD student at the University of Birmingham. Me and my supervisor David Oswald from the University of Birmingham presenting for you today our work in Secure. This paper is an attack-oriented paper. We analyze vulnerabilities in URI scheme handling in Android mobile browsers. Mobile browsers have schemes. Schemes can be categorized into web schemes and local schemes. Web schemes are a protocol that use it to communicate with online endpoints like HTTP, HTTPS, and FTP, while local scheme operates on the machine itself and normally do not require internet connections, like data, Java, script, and file. As seen in the picture on the right, the file schemes use it to access the internal storage of the devices. Since less attention has been paid from academics to local schemes, we mainly focus on them, especially on the mobile context. They rely on different device resources to operate and require substantial changes to work in different platforms. Therefore, in this work, our research question seek to investigate if differences in OS characteristics and context between desktop and mobile rise in new vulnerabilities or not. Our work presents three main contributions. The first one, we found a self-access attack affects most Chromium browsers, including Google Chrome and Edge. This is because of the improper sanitization of the JavaScript URI scheme. Second, we found an origin spoofing issue in data URI that allows abusing it for phishing attacks. This issue affects Samsung Internet only. Finally, we found a file URI issue that led us to a privilege escalation issue in Samsung device that allow an arbitrary app to gain full read and write access to the device internal storage without user consent by passing the dedicated Android storage permissions. All these issues discovered in this work were reported to the proper channel and received in total around 5 CVEs from Samsung, Opera, and Google. The Google CVE is still in progress of release. We will use these contribution orders as an outline for our presentation. So we start our analysis by selecting 15 popular mobile browsers and studying how they handle these local schemes. Here are our findings of a browser support for JavaScript, data, and file scheme. Starting with JavaScript scheme, it's interesting that Chromium browser allow executing JavaScripts, but use clip trim methods to trim the JavaScript prefix of the URI if pasted from the context menu. This is essentially deployed to prevent XSS attacks. Surprisingly, Android has different input methods other than context menu. Among them is IME keyboard, which bypass the trimming restriction. An adversary can trick user into copy-paste a malicious JavaScript scheme into the browser using IME keyboard. IME keyboards are standalone components. They are very popular and sometimes can pre-install in devices like Google Gboard on Pixel devices and Samsung keyboard on Samsung devices. So patching all of them is not a solution. They do not expose like text-passed events so we can handle them. So crucially, this makes the attacks difficult to fix. Secondly, investigating data URI shows us this finding. Here is a screenshot of rendering data URI in two browsers, Chrome and Samsung Internet. So think for a second. Can you spot any differences? So you're probably right. So given the same URI, we notice that Samsung Internet display the last characters of data URI, which result in an origin spoofing issue. As seen in the picture on the right, the page seems served from Facebook.com. Adversary can craft a data URI that impersonate an origin and trick user with it. We report this issue to Samsung and they confirm it. Finally, our analysis for file URI shows us a privilege escalation issue in Samsung Internet that allows us to read the internal storage without Android storage permission using file URI by selecting deny and .ask again option. So we tracked this issue and found a flow in file URI restriction at the application level. However, how Samsung Internet as an app itself can access the storage without the dedicated storage permission was unclear. Therefore, we perform a combination of static and dynamic analysis to find the root cause. So we identified that Samsung Internet relies on Keras browser engine to handle URI scheme requests. Therefore, we set up a dynamic analysis using Frida to debug Keras browser engine. This was our setup. We inject Frida gadget into Samsung Internet and instrument the gadget from Frida module in the PC over ADB. So the core challenge here is Keras. Keras' lack of compilation samples. So it was unreadable. It was non-readable. So to overcome it, we had to hook native file access syscalls like open directory and open. As you can see in the terminal log below, while accessing files using file scheme, we can see usage of these syscalls. We conclude that Samsung Internet as an app itself has access to the internal storage and does not rely on other apps or app component for this access. So looking at the app's effective permission and groups, we found that Samsung Internet, once installed, became a member of the group 1015 SD card RW. According to Android, any member of this group have read and write access to the internal storage. But the question is, how did Samsung Internet get this permission? So after further analysis, we found that Samsung Internet used sensitive data protection SDP NOx module. Apparently, any application that utilises SDP can be a member of SD card RW group. SDP does not authenticate the application that subscribes to it. Therefore, any application within Samsung devices can have full read and write access to the internal storage. We therefore attempt to exploit SDP. To bypass Android storage permission, we deploy a POC that can be installed alongside Samsung Internet. The POC can access the internal storage without Android storage permission. So let's watch the demo. So here we have a Samsung device, have Samsung Internet already installed in it. We will start first by installing our POC to Samsung device. So we wanted to see that our POC can work alongside Samsung Internet and does not interfere with it with the installation. So the installation is complete. Now we will check the packages of these applications. So we'll use Package Manager for that. All right, these are the packages. So Samsung Internet have this package name with postfix as a browser, and our POC have similar package name with postfix just browser. So just a single character can make these packages unique. All right, so we wanted to test that our POC can have the ability to read and write without the internal storage permission. So we will create some file, like a one file, call it secret read, and we put in it like some content. Like for example, this is a secret with some random number like 8778, right? So we'll save that file with name secretread.txt. All right, the file is created. Let's check its content. So you can see this is the same content that we create. All right, so our POC will read that content and print it into the logcat. So we will clear first the logcat. All right, and then we will watch the logcat using our special tags. All right, everything is set up. Let's check our application storage permission or any permission. So no permission is granted, not even the storage permission. Let's launch our POC. All right, we get some logs. Cool. Let's check the node directory. All right, another file is created. Let's check the logs. We can see a lot of groups here. So the interesting one is SD card RW group 1015, like read, write, access to the internal storage without the storage permission, the one from Android. Cool. Now let's see other stuff. So we can see that our application read that file secret read, and this is its contents. Let's check it. Yeah, perfectly match. Cool. Also, our application create another file called secret write. This file was not there. Let's check its contents. Yep, so some content in it, which means it's able to write to files as well. So overall, we can see here that our application can have read and write access to the internal storage without dedicated permission. Now let's talk about mitigations. For mitigation, we propose the following. For the self-XSS attack, after carefully reviewing how IME keyboard worked, we found that it's possible to attach a handler to the address bar text field to detect text changes. We proposed this solution to Google, and Google adopted and deployed a fix. For data URI, defining a standard of how URI need to be viewed is essential for that case. Samsung therefore fixed the issue by showing the leading characters of the URI similar to other browsers. For file issue, we were not involved in Samsung mitigation plan. However, we estimated that the issue required applying a fix on the Android OS level or Knox SDK level. Overall, based on the discovered issue, we can finally say that differences in context do give rise to new vulnerabilities, as these issues target different and unpredictable input methods, UI, and Android SDK and components. Therefore, additional testing methods and automated testing are needed to inspect these issues in the future. So thank you for watching and wish you a good day. Thanks.